5.2 sigma notation. And limits of finite sums. So sigma notation, we're going to need this for, eventually we're going to find the actual area underneath the curve, and it's going to be awesome. So sigma notation. So the summation, what this summation is this is that Greek letter E, sigma. So it looks like this. The summation as k equals 1 to n of a sub k is equal to, well, what we do is we just add up consecutive terms. So this is going to be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus, until we finally get to a sub n. So then you'd have like 1 below n, and then finally plus a sub n. So plus a sub n. So when we're looking at these, here's kind of our I'm going to kind of label all these so we know what they are. So this symbol right here, this sigma notation, is it's a summation symbol. This is a summation symbol. This k is the index. So the index k starts at 1. And up here, this n says that the index k ends at k equal n. This right here, this entire formula of a sub k, is the formula for the kth term. This is the formula. For the kth term. So let's do some examples. It's really pretty straightforward. What this is going to allow us to do is it's going to give us a way to shortcut things. So example, probably your most trivial example would be determine the sum. So the summation as k equals 1 to let's say 6 of just k. So our formula k just means we're going to have 1, 2, 3, 4, 5, 6 terms, and what I'm going to do is I'm going to plug 1 into this formula. So when you plug 1 into this formula, you just get 1 plus. Then you're going to do it all the way till we get to 6. So you're going to plug in 2, and then you're going to plug in 3, then you're going to plug in 4, then you're going to plug in 5, and then last you're going to plug in 6. So what we're going to do is we're just going to add all those up. So it's going to simplify to 21. B. The summation of k equals 1 to 4 of minus 1 to the k multiplied by k squared. So what I'm going to do is I'm going to have 1, 2, 3, 4 terms, because I start at 1 and end at 4. So the first term I'm going to plug in k equals 1. So minus 1 to the 1 times 1 squared. And then I'm going to plug in 2 next. So minus 1 squared times 1, not 1, but 2 2 squared. So make sure that we know that you know your k is right here, right? So this is your k. So first we plugged in k equals 1 into those locations, and then we plugged in k equals 2 into those locations, and now we're going to plug in k equals 3 into those locations. So plus minus 1 cubed times 3 squared, and then finally minus 1 to the 4th times 4 squared. So plugging k into each one of those, into that location. So when we get this, well, minus 1 to the 1 is negative 1. So negative 1 times 1 squared is 1. Now negative 1, negative 1 times 1. Now negative 1 to an even power is just going to be positive 1. So this is 1 times 2 squared, which is 4, so plus 4. Negative 1 cubed is going to be negative 1. So this is plus 9. And negative 1 to the 4th is positive 1, plus 16. So we have, this should have been minus. This should have been minus. So what this negative 1 to the k does is it makes the signs alternate. So minus, plus, and so on. So if it was minus 1 to the k plus 1, the first one would be plus, and the next one would be minus. So when I add these together, this is going to be 3 plus 7, so this is 10. Let's see. Summation from k equals 1 to 3 of k all over k plus 2. So again, remember that your k is essentially your input. It's just a function. So you're just going to add the function together, but you're going to evaluate it at, at first 1, then 2, then 3. So 1 over 1 plus 2. So that's when k is equal to 1. So we're starting at 1, so when k equals 1. You know what I should do? Let me erase this. You don't have to start at 1. Let's go k equals 2 to 4. Because there's no reason why, actually let's start at k equals 0. K equals 0 to 3. So when you plug this in, first we're going to plug in, we have 0 and 0 in those locations, so 0 all over 0 plus 2. And then I'm going to plug in 1, so 1 over 1 plus 2. And then I'm going to plug in 2, so 2 over 2 plus 2. And I'm going to plug in 3, so 3 over 3 plus 2. So what we get here is 0 over 2 plus 1 over 3 plus 2 over 4 plus 3 over 5. So when we simplify this, that's just 0, so I can go away. So common denominator looks like 60. So 20 over 60 plus 30 over 60 plus 36 over 60, which is equal to 86 over 60, which is equal to 43 over 30. Alright, so there are some rules for summations. What is nice is these are the very similar rules that we've already seen before. One, sum rule. The summation from k equals 1 to n of a to the k plus b to the k. Well, the summation of the sum is the sum of the summations. You guys are seeing a common pattern here. We saw this with limits. We saw this with derivatives. We saw this with antiderivatives. Also, there's the difference rule, and I could have probably put it in the same line. So the summation from k equals 1 to n. Let's see. Of a sub k minus b sub k is going to be equal to the summation from k equals 1 to n of a sub k minus the summation k equals 1 to n of b sub k. So the difference of the summation is the sum. The summation of the difference is the difference of the summation. 3. Constant multiple. So the summation as k equals 1 to n of c times a sub k. Well, what do you think we can do with constants? Well, we can pull them out just like we do with limits and derivatives and indefinite integrals. Oops, pull out the c times a sub k. So, like I said, we can pull out the constant. And the constant value. This is to give us a shortcut to determine the summation of just a number over and over again. So if I have the summation from k equals 1 to n of just c, this is just equal to n times c. Because there's no input here. This is just a constant. So what you're going to have is, if I had like a kind of example of this one. An example, if I had the summation from k equals 1 to 4 of just 5, well, we plug in 1. Well, there's no k value. There's no input to this function essentially. So you plug in 1, you're going to get 5. You plug 2 into here, you're going to get 5. You plug 3 into there, and then you plug 4 into there. Oops. And you plug 4 into that same function, so you're still just going to get 5. So that means the summation from 1 to 4 or 5 is just 4 times 5. This is equal to 4 times 5. So you get 20. Alright, so what I want to do is I want to use these rules for these finite sums, and these rules are going to become helpful when I eventually find the actual area of a curve. So using the rules. So this is all just to be able to find the area of the curve. This is kind of what we're setting up. Eventually you're going to use this in differential equations as well. But yeah, this is a kind of a big setup for some of the rest of the math. All right, so what I know is remember I made you guys do that with limits. I made you do the limits like for quizzes and exams. I'm going to make you do this here as well. And what's nice is these rules are very similar to the same thing. So I know the summation of the difference is the difference of the summation. So this is going to be the summation from k equals 1 to actually, do I have? I didn't give you common sums. Let's see if I have them here. Yeah, let me before I do this, let me jump together. Let me give you some common sums. So, and then we'll be able to see if I can put it. No, it's gonna have to be here. All right. You know, I'm gonna undo that. I'm gonna do. Come on. Can't unerase. There we go. Okay, so I'm just going to make a new page and come back to that one. All right, common sums. So the summation, k equals 1 to n, of just k is equal to n times n plus 1 all over 2. And I don't remember if you... I'm not sure if you remember the classroom, but I actually had these common sums written on the wall because it's not something I would, even in class, force you guys to memorize. So this is the very first common sum, and I'm going to show you how this was done. So the story was told to me by a math professor that Gauss actually did this in, I think it was in elementary school or middle school. So what his teacher asked him to do, so that I'm going to kind of do what he asked. He asked all the kids to add up the first 100 numbers. So 1 plus 2 plus 3 plus 4 plus 5. You want to do it to 100. So clearly he probably was grading some papers, and he gave him some busy work. So this is what Gauss did. He said, okay, well, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus, and he didn't write them all out, but then you know that you're going to have plus. Let me erase some of these because I want it to look pretty. Plus dot dot dot, and I know I'm going to have plus 97 plus 98 plus 99 plus 100. So this is basically what we're doing. So he says, well, what if I flipped them around? I know that this would be the same thing. So what if I did 100 plus 99 plus 98 plus 97 plus, dot 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 plus 4 plus 3 plus 2 plus 1. So now you know that each one of these lines are equal. So let's add them vertically. Because addition is, since addition is commutative and associative, I can add in any order I want. So I know if I add this and I add this, I'm going to get double what I need, but I can always divide things by 2 quickly. But if I add this column, I get 101. If I add this column, I get 101, and then 101, and then 101, and then, 101, and 101, and 101, and then 101. So we know that we have 100 101s. So this is going to equal 100 101. So 101 times 100, boom. Now I want this value, so I have to take that. Let me erase this a little bit. So what I have here is I have 100 times 101. But I don't need that. I need half of that, so I'm going to divide it by 2. And what we can see is this number up here, n times n plus 1 divided by 2, n times n plus 1 divided by 2. So if I were to sum up the first 100 digits, n would be equal to 100. So you just pop it in this equation. It's very clever. So Gauss is one of the most prolific mathematicians. But for what I heard, yeah, you'll have to read up on him. I don't want to talk ill about something that I really don't know, but I heard wasn't the nicest. Okay, number 2. So the summation k equals 1 to n of k squared. This is equal to n times n plus 1 times 2n plus 1 all over 6. Now I'm not going to prove this one. It can be proved using that, but it's a little long. And then the last one is the summation from k equals 1 to n of k cubed. And this can be found using these as well. So this is going to be n times n plus 1 all over 2 squared. So those are our common finite sums. So let's go back to our problem, because what I wanted to do is I wanted to use the algebra rules along with these common finite sums to find the summation of these things. So let's back out of here and go to this. So back to this. What I want to do is I want to using the finite sum rules and common sums to simplify. Alright, so I know the summation of the difference is the difference of the summation. That's what I was trying to pull off. So this is going to be 4k squared minus the summation from k equals 1 to n of just k. Now what I know I can do is I can pull out constants, so I can pull out that 4. So this is 4 times the summation from k equals 1 to n of k squared minus the summation of k equals 1 to n of k. Now what we're trying to do is I'm trying to get one of 3 things. I'm looking for stuff that looks like this. The sum of k, or the sum of k squared, or the sum of k cubed, or even the sum of some constant. Like I know those things, so I guess I can go back to my summation rules, And I can write the fourth one, which probably should be the first one. But so the summation from k equals 1 to n of just a constant is n times c. So I know I already had this, but this is equal to n times c. So what I'm looking for is I'm looking for these things so then I can turn them in terms of n. So here I have this. I have this one's a k squared, so I got that one. This one's a k, I got that one, so I know these sums. So this is going to be equal to 4 times, well, k squared was equal to, should be n times n plus 1 times 2n plus 1 all over 6. And for minus the summation of k would be equal to n times n plus 1 all over 2. And I'm not simplifying any further, I just wanted to turn them into n's, okay? There's going to be something we're going to do a little bit later to kind of work on this. B. Summation k equals 1 to n of minus, so in parentheses, okay. So what I know is the summation of the sum is the sum of the summation. So this is the summation from k equals 1 to n of minus k cubed plus the summation from k equals 1 to n of 7. Now also I can pull out constants, so this is going to be minus the summation from k equals 1 to n of k cubed plus the summation from k, well actually I already know this answer too, so I'm going to simplify this one. So this one's done. I have it set up. Now this one is going to be equal to, well this is a constant, so this is going to be 7 times n. Now turning this in terms of n, k cubed is that n times n plus 1 all over 2 squared plus 7n. So now I turned everything in terms of n as opposed to k. We were going to get some practice with this, okay? So I know it seems a bit much right now, but it won't be bad. We'll get used to algebraically manipulating these things. All right, so let's do one where we have some problems. So what about something like this? Let's put a number in there, and maybe this makes a little more sense. What if I say the summation from k equals 1 to 4 of 3k squared plus k minus 2? Let's do that. All right, so I know that this thing is going to simplify to, the sum of the sum is the summation of the sums, plus I can pull out constants. So this is going to be 3, maybe I'll do it all in one shot. I don't want to skip things. So this is going to be the summation of 3k squared plus the summation of k minus the summation of 2. I know that's a thing right there. Now I can pull out constants, so I can take that 3 and pull it out. So this is going to be 3 times the summation from k equals 1 to 4 of k squared plus the summation from k equals 1 to 4 of k minus the summation from k equals 1 to n of 2. I know you could pull out a 2 and have 1 left over, but since this is a constant, I already know the formula is just 2 times n here. So when I set this up, this is going to be equal to 3 times, well, remember what k squared was. It was n times n plus 1 times 2n plus 1 all over 6. But remember what n is. N is equal to 4. So instead of writing n's in there, I'm going to go back and write 4's in there. So this is equal to 4 times 4 plus 1. 2 times 4 plus 1 all over 6 plus this is going to be k. Well, k is, remember what it is, it's n times n plus 1 all over 2. but instead of n, we're going to have 4's there. So this is going to be equal to 4 times 4 plus 1 all over 2. Plus this is just 2 times n. I'm sorry, I should have an n there. I should have a 4 there. 2 times 4. So this is just going to be 4 times 2. Alright, now simplifying. This is 3. Actually, I can do this. This is going to turn into 2, right? So I have the top is 4 times 5 times 9 all over 2 plus 4 times 5 all over 2 plus 8. So 45 times 2 is 90 over 2 plus 20 over 2 plus 16 over 2. It's going to be 110, 126 over 2, which is going to be equal to 63. Alright. Finally, we get to we have to find the actual area underneath the curve. So going back to the our old friend, y equals 1 minus x squared. So remember, the area under the curve of y is equal to 1 minus x squared on the interval from 0 to 1. So when we were setting up areas, we knew that the area for n rectangles is, we know that your change in x is equal to b minus a all over n, where n is the number of rectangles. And we also know when I want to find these heights that, you know, our area ended up being this. It was f of x1 plus f of x2 plus f of x3 plus f of x4, and this was just for 4 triangles multiplied by your change in x. So notice how I have a summation here. I can actually rewrite this as the summation of f of x sub k multiplied by your change in x. So this would be k starts at 1, and in this case goes to 4. So I can write that as that summation. So what I want to do is I don't want to use 4 rectangles anymore. What I want to use is I want to use all the rectangles. I want to use an infinite number of rectangles. So instead of saying stopping at 4, what if this just kept going? Plus dot 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 plus fx sub n times your change in x. So what if, so this would just be n rectangles. So the only difference is instead of this thing stopping at 4, this thing is going to stop at n. So this is going to stop at n. So what I'm going to do is I'm going to use right endpoints all the time. And here's my reason why is, since we're going to take essentially we're going to take an infinite number of rectangles, and as the rectangles get smaller, because we're taking more of them, your left and right endpoints essentially converge. So if you did the left endpoints and you took an infinite amount of them, or if you took the right endpoints and took an infinite amount of them, you're going to get the same area. So just for ease, I'm just going to use right endpoints all the time. And what that allows me to do is, once I find my change in x, because what I know I have here is, if I have my my curve, this curve, I'm going to kind of stretch it out a little bit because I need to write some stuff in here. So there's my 1 minus x squared. Now, I know that this is 0, but the very first number is your change in x. I know the next number was 2 times your change in x. and then so on, 3 times your change in x. Now there's some number out here, and I'm just going to call this is going to be my function using right endpoints, and this is going to be the kth rectangle. So what that means is this right endpoint is just going to be k times the change in x. So this is your general rectangle, because what I need to do is I need to find a general function that we're going to be taking the summation of. So I don't want the nth one, I need the kth one. So somewhere in here is going to be an f sub k. So I'll kind of show you what I mean by that. So in here is plus dot 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 and plus fx sub k plus dot 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 plus fx sub n times your change in x. So if I have this function, when I plug in 1, I get this thing. When I plug in 2, I get this thing. When I plug in 3, I get this. When I plug in n, I get this. So this right here is my general term. This is my general height term. And that happens at x sub k. All right, so this value right here is, you have, this essentially is x1, this is x2, this is x3, dot, dot, dot. This value here is going to be equal to x sub k. Now your book likes to call it c sub k, and it doesn't matter if you want to use x sub k or c sub k, they basically represent the same thing. So this is that right endpoint of that general rectangle, and we're gonna need that in order to find these things. So I need this kth rectangle is really what I'm looking at, and I need all the points in it. Well, I need to know what its right endpoint is, and then eventually I need to know its height, which is going to be plugged into the function. Okay, so once I have that, so the book likes it like this. They actually write f of c sub k times your change in x. And they say change in x sub k as well. And the reason why they say x sub k is because you don't have to have the same width for all your rectangles. So your widths could change throughout your interval. But for simplicity, you don't. You just keep them all the same. So instead of me writing x sub k, I'm just going to write change in x, okay? Since the widths are all the same, they're all equal to each other. So this is essentially what the book writes. So what I need to do is I need to come up with an expression for that. So what's nice about this is I know that we can find all these values. The reason why is I know what the change in x is. It's right here, and I know exactly what it is because I have this interval. So I know this change of x is going to be equal to 1 minus 0 all over n, so this is going to be equal to 1 over n. So I know this value. That's 1 over n. Now your c sub k is nice because your c sub k is just k times your change in x, because I'm using the right endpoints and we're doing it for simplicity. So that means your c sub k is just k times 1 over x. I'm going to erase this general term here. I'm going to erase it. So your c sub k, and even on the test, is always going to be that way. So your c sub k is going to equal k times your change in x times the change in x. So k multiplied by this, k times 1 over n, is equal to just k over n. So whatever your change in x is, just throw a multiplication of k. So the k, you're just going to add an extra factor of k in the numerator. So this term right here is going to simplify the summation from k equals 1 to n of f of k over n multiplied by your change in x, and your change in x is 1 over n. So multiplied by 1 over n. Now the order in which we do this is important. So you have to evaluate f before you multiply, because you're not multiplying these two pieces. This k over n is being plugged into f, so you have to take care of f before you take care of this 1 over n. So you have to do f first and this 1 over n next. So doing that, plugging it in first, evaluating first, multiplying second. again, evaluating first, so this is going to go in here. So this is going to be equal to 1 minus k over n squared times 1 over n. So we have to evaluate first, and then we'll multiply second. So before we multiply, I got to simplify all this stuff. So this is going to be equal to the summation k equals to n of... Kristen, I'll take care of it. I'll take care of it. 1 minus, this is going to... You want to open and close one more time? Sometimes it gets a bugger. It's not a big deal. So over n squared, and this is going to be times 1 over n. So multiplied by 1 over n. So when I simplify this, this is going to be equal to the summation from k equals 1 to n of... what I'm going to do is, now that I've taken care of the parentheses, so when you simplify things, it's just order of operations. So the first thing you have to do is evaluate. You got to get rid of the f. The next thing you got to do is just order of operations. So powers first, multiplication second, and then we'll do addition next. So this is just going to multiply to here and then to here. So what I have is 1 over n plus k squared all over n cubed. All right. Okay, so that's what we're looking at. Now what I'm going to do is I'm going to do the summation rules, because there's nothing else I can do. I can't subtract these things because they're not like terms. So I'm going to apply the summation to each one of these. So the sum of the difference is the difference of the sum. So this is the summation of 1 over n minus the summation of k squared all over n cubed. So k equals 1 to n. Now remember, since n is right here, n is a constant. N is some number. So if n is equal to 4, this would be a fourth. So what I know is that n is a constant, so 1 over n is a constant. So I know this value. Since this is the summation of a constant, I can just multiply these things together. Now, n cubed is a constant, so what I can do is I can pull out that 1 over n cubed. So it was 1, this is going to be n, and this is going to be 1 over n. The reason why I'm leaving this is because it's already one of those things. It's a summation of a constant. Now, I want this thing to look like the summation of k squared. So that means that 1 over n cubed has to come out. 1 over n cubed has to come out, and now I have the summation of k squared. So I'm trying to get those, those 4 common sums that we talked about. All right, now I can turn these things all into n's. When I multiply this is just going to be n times 1 over n. And then I'm going to subtract, when I do this is 1 over n cubed, and squared is going to be, it's n. N times n plus 1 times 2n plus 1 all over 6. So we're going to simplify this up. This is just 1. N over n is 1. Minus. I'm going to cancel one of these. So one of these are going to cancel with this 3 to turn it into a 2. So the top is going to be equal to 2n squared plus 3n plus 1. I'm just foiling that. All over 6n squared. So that represents the area given whatever rectangle. So what I'm going to do a quick check here. So check. What if n is equal to 4? So remember, we did right endpoints for 4. So this would be equal to 1, and then it'd be 1 minus, so 2 times 4 squared plus 3 times 4 plus 1, all over 6 times 4 squared. And now we kind of really hope that this is going to be the thing. So this is going to be 32 plus 12 plus 1, all over 664, 42, 43, 1 minus 43. Boy, I remember that. This is 1 minus 43 over 64. I'm almost sure this is what we're looking at. So I got 21 over 64, is that right? Oh, this is 96, I was off. That's 96, that wasn't right. So 96 minus 43 is going to be 53 over 96. So 0.552. Did I actually calculate that? Let's see if I didn't screw that up. 2 times 16 plus 12 plus 1 over 6. Okay. Feeling pretty good about that. Six. 2 times 16 plus 3 times 4. 40. That's bad. 45. 51. Which is equal to 0.53125. We did that. Yep. Oh, sorry. It's going crazy. Stop. Thank you. There we go. So 5. Yep. There you have it. That's the number that we got. Now, what's kind of clever here is this is the area under the curve using any rectangle that I want. So if I plugged in 8, I'd get a better answer. If I plugged in 16, I'd get a better answer, or 17, or 18, or 19. So what I'm going to do, in order to find that actual area, I am going to, I'm not going to use 4. I'm going to use infinity. So our actual area, the area under the curve, is going to be equal to the limit as n goes to infinity of the summation from k equals 1 to n of f sub c sub k times your change in x. So technically, this is not the area, this is the estimated area. This is an estimate. So if I want the actual area, I need to take an infinite amount of rectangles. Because the more rectangles you do, the better you get. So if you do an infinite amount of rectangles, it's going to be perfect. So what I'm going to do is I'm going to take the limit as n goes to infinity of this expression I just found of 1 minus 2n squared plus 3n plus 1 all over 6n squared. And the limit of the sum is the sum of the limits. So the limit of 1 is 1. Now when you take the limit of this, I know I could use L'Hopital's rule. And what you're going to do with L'Hopital's rule is the derivative of the top would be, so this would be minus the limit as n goes to infinity. So I think we know that this is just going to be 2 over 6. But L'Hopital's rule will work. You just have to do it twice. So this is going to give us, I'm just going to erase it. We know it's going to be 2 over 6. So minus 2 over 6. So 1 minus a third, which is equal to 2/3. So that's the actual area underneath that curve. All right, I know that was a rough one. So let me just pick an odd one out of the book or an even one out of the book, and do one more. Because I'm going to ask you to do that on the test, but I'm going to ask you to do it on a quiz first, just to make sure you guys can. I want to look over your work. I want to see how comfortable you are. Let's say 48. Is it off?